myself Kavita. I'm from the Department of Mathematics. Now in this video we are going to learn about a series of real numbers. In this chapter the first thing we are going to cover a few topics about introduction, series definition, examples of series, convergence, divergence and oscillatory series. Example for convergence, divergence and oscillatory series. Condition for the convergence series. The first thing we are going to learn about the introduction part. Here Newton and the Leibniz two person, when they expressed the integrand function in the form of polynomial, it contains infinite number of terms. So this helped them to overcome the problems when they were facing through the integrations. And even when they applied the algebraic expressions like addition, subtraction, multiplication, division, this helped them overcome the problems which they were facing, to the errors which they were occurring through the solving infinite number of terms. So this came to the existence of the series. This gives the basic idea for your series. Next thing, what is series? Series is nothing but the addition of all the terms in the sequence. If you here we are taking one sequence, u1, u2, u3 and so on. This is a sequence. If you had all the terms in this sequence, that is u1, u2, u3, these are called the terms. If you had all the terms in the sequence, this is called the infinite series, or generally we call it as the series, and it is usually represented by summation n runs from 1 to infinite un, or generally summation un. And this is called this is whatever u1 u2, these are called the terms of the series, and here un is called the nth term or the general term of the series. Next we are going to see about this series. If you had all the series, this does not give any meaning at all. Therefore we are that is your addition of the sum of infinite series is simply the addition of all the terms of the series, but it does not give any meaning. Therefore we are associating all the addition of the terms with your sequence, that is your Sn. Sn is equal to u1 plus u2 plus u3 plus and so on un. This is called your sequence in terms of the series and series. Next thing we are seeing about this infinite number of series cannot be solved directly with using the sequence. Therefore we are using SOPS method, that is sequence of partial sums method. Here we are taking individual sequence with individual series and equating and finding the values. So here first one S1 is equal to U1, this is called the first partial sum, and S2 is equal to the addition of the two series, that is U1 plus U2, the second partial sum, and so on. And like that we can also find n number of partial sums. Here S1, S2, whatever S3 we are taking, it is considered as an infinite series. It generally gives an given infinite series. It gives approximation to your infinite series. Next thing we are going to see about the example for that is your visual proofs of your convergence series. Visual proofs of your convergence series is nothing but how we are expressing, that is we are going to express our series in terms of the terms of the series. That is, here we are using the summation symbol. This is called summation symbol. Here it starts from n is equal to 1 to infinite. In generally we are taken it as 1 by 2 power n. This is nothing but un or an. If you substitute n as 1, you will get 1 by 2 plus 1 by 2 square, plus if you substitute n as 3, you will get 1 by 2 cube. If you substitute n as 4, you will get 1 by 2 power 4 and so on. So this is summation symbol is used to addition. Here we are using addition in between that. This gives your series sequence, as well as the addition of all the terms in the series. So this can also be expressed, that is expanded, by using 1 by 2. There is no expansion, so we will write 1 by 2. 1 by 2 square can be written as 1 by 4. 1 by 2 cube can be written as 1 by 8. 1 by 2 power 4 is nothing but 1 by 16 and so on. Like this you can easily solve the problems while if they are given in number in the term, you can expand in terms expression, you can expand in terms of the series and you can solve the problems. Next thing we are going to see the example for your convergence series. You are taking one series, that is your 1 plus minus 1 plus 1 minus 1 plus and so on plus minus 1 power n plus 1. So this series, it is in series, and here your first one is u1 and minus 1 is u2, 1 is u3 and minus 1 is u4 and so on. Here it is the terms of the series. First thing we are going to equate it with your sequence, that is your Sn. Next this series can be solved using SOPS method, that is your sequence of partial sums method. Your is equating individual term with your series and you are finding the values. First one S1 is nothing but U1 is your 1. Next one is S2, S2 is nothing but U1 plus U2, that is your 1 plus into minus is minus, 1 minus 1 which is equals to 0. Next thing is S3, S3 is nothing but U1 plus U2 plus U3 which is nothing but 1 minus 1 plus 1, 1 plus 1 minus 1 get cancelled, will get your 1 and so on. This is how we'll find out the series. And one thing you can also observe that here S1 and S3 both are odd numbers, you'll getting the answer as 1. If it is even, that is S2, S4 if it is on even and so on. If it is even, you will be getting the answer in terms of 0. That is, the answer varies from odd numbers to even number. If it is odd, you're getting the answer as 1. If it is even, you're getting the answer as 0. That is, the series is oscillating between two finite values. In generally, we are representing in terms of nth value, that is your nth sequence is 1 plus minus 1 power n plus 1 divided by 2. When you take n as 1 here, it becomes minus 1 power n plus 1 which is nothing but 1 plus 1 minus 1 power 2. 1 minus 1 power 2 is 1, 1 plus 1 is 2, 2 divided by 2 is 1. And if you take n as 2, minus 1 power 2 plus 1 which is minus 1. If you take 1 minus 1 is 0, 0 by 2 is 0. This is your general representation of your terms of the series. So this is how we find out the problems when they are given the series by generally solving this. Next thing, this series, this sequence, whatever we are solving, it not only tends to finite limit, it is also even tending to finite limit. So if it is finite limit, what happens? If it is infinite limit, what happens? We are studying now. Here, if it is finite limit, we are going to solve with your convergence of the series. If it is infinite series also you are tending, but it tends to finite values, that is called convergence series. In this, what we are going to solve means we are going to take a sequence. In this sequence, we are going to express nth partial sum sequence and we are apply the limit to this sequence. If this sequence tends to infinite or if its sequence tends to finite values, that finite value we call it as the convergent series sequence. If sequence is convergent, we can say that the series is also convergent. Here we have taken the sequence S and it tends to, if it is finite limit, that finite limit is called the sum of the convergent series when after applying the limit as n tends to infinite. In terms of S and we have substituted a summation here, that is your series, and you'll get your finite value. This is should be unique. Then we say that the series is a convergent series. So now we are studying the example for your convergent series. Next, you are taking that series 1 by 1 into 2 plus 1 by 2 into 3 plus 1 by 3 into 4 plus and so on plus 1 by n into n plus 1. This term does not have any meaning. Therefore, we are associating it with the sequence, that is your Sn. When you associate it with your sequence, it becomes Sn is equal to 1 by 1 into 2 plus 1 by 2 into 3 plus 1 by 3 into 4 plus and so on plus 1 by n into n plus 1. This problem we can solve by using the simple partial fractions method. This 1 by 1 into 2 can be written as 1 minus 1 by 2. If you cross multiply 2 ones are 2 minus 1 by 2, you'll get back to your expression, that is 1 by 1 into 2. Again 1 by 2 into 3 can be written as 1 by 2 minus 1 by 3. If you cross multiply and solve this, 3 minus 2 divided by 3, 2 into 3 will get back your this section. The last term, that is 1 by n into n plus 1, you are split it in terms of partial fraction by using this 1 by n in minus 1 by n plus 1. And when you remove the brackets here, minus 1 by 2 plus 1 by 2 minus 1 by 3 plus 1 by 3, everything get cancelled. The leftover term here, the first term is 1 and the last term is 1 by n plus 1. And when I apply the limit as n tends to infinite, here this value becomes 0. The leftover term is 1. This is your finite value and it is also unique. Therefore, we say that the sequence is convergent. If the sequence is convergent, we can also say that the series is also convergent. This is how we find out whether the series is convergent or not. Next thing is divergence of the series. The series is convergent. That is, it is tending to finite limit. Here the series is tending to infinite limit. If the sequence Sn has no finite limit, then we say that it is tending to divergent, and it may diverge to plus infinity or minus infinity. If the sequence diverges to positive, we can tell it as it is diverging positively. If it is tending to minus infinity, we call it as it is divergent into negatively. So to solve this, we have taken the fun example. You can see, take the series 1 plus 1 by 2 plus 1 3 plus and so on up to n. Here in general we represent it as summation n. Your Sn in generally you are representing Sn is equal to n into n plus 1 by 2. It is your partial sum. That is your, if you substitute n as 1, 1 plus 1 is 1 plus 1 is 2, 2 by 2 is again your 1. Next n is 2, 2, 2 plus 1 is 3, 2 by 3. Yeah, 2, 2 into 3, this is 2 plus 1 is 3, 2 by 3, 2 get cancels, you get back your expression this. So when you apply the limit as n tends to infinite, you will get back infinite into addition of any infinite terms also infinite, and multiplication even in division is also infinite. Therefore the divergent of the series, it is tending to positive value. Therefore this series is tending to plus infinity. It is a divergent positively. We can even prove that it is a convergent series also. And oscillatory series, it is nothing but it is neither convergent nor divergent. It is neither converging to positive finite value, it is neither diverging to negative value. It is oscillating between two finite limit, that it may finite, or it may oscillate between any two finite value, or it may even oscillate between any two infinite values. Next thing we are going to see the loss of the series. What is loss of the series means? So we are using simple definition method, we have solved the some problems of some series and some convergent series. What is divergent series also? Yeah, this loss helps us to solve the problems. If it is not only one series, if they are given 2, 2, 3 and so on, the type of series if it is given, we can solve this method by not only solving one series, you can solve at a time. Here they are given two series, that is summation n runs from 1 to infinite an and summation n runs from 1 to infinite bn. These two series are convergent series. When you add these two series, or even when you subtract these two series, when you add and even subtract these two series, you will get your summation n runs from 1 to infinite an plus bn. But directly you can solve this method for addition and even subtraction method. For if it is scalar multiplication, if you multiply any one series, that is series summation n is equal to 1 to infinite an by any scalar value c, and that is also results into c into summation n runs from 1 to infinite an. This is also gives your exact value. If it is series convergent or divergent, both will convergent and both will divergent. This type of problems will be applicable only for the addition on multiplication, multiplication for scalar value, and subtraction. It is not applicable for two series multiplication or two series division, not for the exponential terms also. Next, to solve these problems, not only definition method is not enough. So therefore we are introducing the geometric series. So this gives you to, this makes your problems to solve very series also. Next thing is we are solving about divergence test. So now we have studied about convergence test. Next we are thinking about divergence test. What is your divergence test? Means here we are taking one series, that is an, that is your nth partial sum, nth term. So if it is not converging to 0, when I apply the limit as n tends to infinite to the series, if it is not tending to 0, then we say that the series summation n runs from 1 to infinite an is divergent. If it is tending to series, then we say that the summation n runs from 1 to infinite an is convergent. And one more note, in many cases we can see that all the sequences converges if you add all the sequences to 0, but when you add the terms it may divergence. We are taking one example here. I have given some few examples here, so let me explain an example here. Summation n is equal to 1 to infinite 1 by n. Your an value is 1 by n. When I apply the limit to this value as limit n tends to infinite 1 by infinite, which is nothing but 0. If it is 0, then it is converges or diverges. It is, if it is 0, we say that it is a convergent series. If it is not tending to 0, we call it as it is a divergent series. These are the few examples for your divergence test. Next thing is geometric series. So geometric series, one main important geometric series, this series not starts from 1, it starts from 0 to infinite. Summation n is equal to 0 to infinite. So the general formula is r power n, which is 1 plus r square plus r cube plus r power 4 and so on. Here into each term we are multiplying by c. C dot Rn plus C into C Rn. That is first term. You can take this R, we call it as the common ratio. Is not your C is your scalar value. Not only this C, you can multiply any number so that this common ratio won't change, and you can solve this type of problem using geometric series. We have introduced this method to because the definition method is not enough to solve all the series problem. Therefore, geometric series problems comes out with a clear result. Therefore, we can solve this type of any different difficult problems using this geometric series method. Next thing is we are deriving about the definition of the that is derivation of the geometric series. So you are generally representing the geometric series summation n is equal to 0 to up to positive value, that is n C into Rn with equating it into that is you are assigning it into Sn. When you expand this, when you substitute C n as 0, you will get C plus C into R plus C into R square plus C into R cube plus and so on plus C into R power n. This is your first equation. If we multiply both the sides, that is your LHS and RHS side by R, in the first equation you will get your R into Sn, which is equal to C into R plus C into R square plus C into R cube plus C into R power 4 plus and so on plus C into R power n plus 1. This is your second equation, and you taking subtracting the second equation with your first equation, you'll get to know that Sn, that is Sn minus R into S power n is your the LHS part. What happens to your RHS part? This CR get cancelled. CR square minus CR square get cancelled. CR cube plus CR cube get cancelled. Everything get cancelled. The left out is your first term C. The last term is C into R power n plus 1. So if you take in the LHS part Sn common, you will be left with 1 minus R. In the RHS part, if you take C as common, you will be left with 1 minus R power n plus 1. Therefore, your Sn leads to C into 1 minus R power n plus 1, 1 minus R divided by 1 minus R. This helps to solve the problems if the problems in terms of common ratio, that is the values are repeating. So that is if the values are continuously repeating. So this helps you solve the type of problems. Next thing is, so there are some certain conditions to they solve this geometric series. If the infinite geometric series, we say that divergence if modulus of R value is greater than or equals to 1. Otherwise, that is we are taking infinite value summation n is equal to 0 to infinite C into R power n, which is equal to C into 1 minus R if modulus of R is lesser than 1. By using the direct formula, you can solve this. So if you remove the first n number of terms, then our series become n is equal to m to infinite C into R power n, which is equal to C into R power n divided by 1 minus R. So this is also convergent. This is also for modulus of R is lesser than 1. You can use this. So same formula can be written as 1 in the first term by using this is your first term 1 minus R. This is a certain condition for your geometric series also. Next, we are going to learn about the P series. So in certain cases, geometric series, all the problems will not be in the form of geometric series. Their common ratios may be also varies. So if that is given, we can solve this type of problem by using P series. So here a P series of the form summation n is equal to 1 to infinite 1 by n power p, which is equal to, if you are substituting n as 1, you will get 1 by 1. If you substitute n as 2, you will get 1 by 2 power p. If you substitute n as 3, you will get 1 by 3 power p plus and so on. So this here the series will be convergent if p is greater than 1 and diverges if p is lesser than or equals to 1. So here some example, let it be example b 1 by 2 power 3. So here p is 3, that 3 is greater than 1, therefore we say that the series is convergent. Let it be 1 by root 2. Here root 2 means 1 by 2, which is nothing but 0.5. 0.5 is lesser than 1, therefore we call it as the series is divergence. By using this simple technique, that is P series method, we can solve the problem very easily. So until now we studied about the definition of the series, convergence of the series, their properties also, and even geometric series also, and even P series. Next thing is comparison test series. What is comparison test series means? So here not only one series, they can even give two series. So solving independent series, that is series summation A and it is convergence, then we have to solve individually summation B and convergence. Instead of that, we can solve one series and we tell that other series is also convergent. That helps you in the comparison test series. So you are taking one value m that is greater than 0, and an, these two series an and bn, that is also both are greater than zeros, and an is less than or equals to bn. There exists some value for n greater than or equals to m. We say that the series summation n is equal to 1 to infinite bn is convergent, then summation n is equal to 1 to infinite an is also convergence. If summation n is equal to 1 to infinite an is divergent, then summation bn n is equal to 1 to infinite bn also divergence. And one more condition is, if bn is divergence, then we cannot say that the test fails. If summation an is convergent, then also this test does not help us to solve our problems. So these are the topics which help us to solve our the series, whether the given series may converges or diverges. So next, thank you.